3rd and 4th grade. Today we are looking at Science Chapter 5, Part 5, Water's Energy. So let's start reading. One day when Ben and his father were fishing, they came to a spot in the stream where the water rushed quickly along. Ben could feel the force of the stream as he waded in. Further downstream was a dam. Here the water stopped flowing and formed a deep pool. Would it surprise you to discover that both the swiftly flowing stream and the still quiet pool contained energy? Well, first we need to figure out just what is energy. So what is energy? If something has energy, it is able to do work. Thus, energy is the ability to do work. Scientists say that work is done when an object is moved. So sometimes you might say, I just don't have the energy to do that. Well, that is not entirely true. If you have the ability to do that work, then you technically have the energy. Sometimes what we're missing, though, is the motivation to do that work. And remember, work is when an object is moved. So it says, are you doing any work right now? Think about that for a moment. If you're sitting at your desk, holding your book, and reading silently, you're not doing any work in the way scientists use the term because you are not moving. Your mind is busy, but it is not moving. If you hold your book up long enough, your arms might get tired, but you are not doing any work unless you move the book or turn the page. So right now, my finger, it's doing work because it's moving, but when it holds still, then it's not doing any work. If you close your book and put it away, then you have done work. So that's energy. Energy is the ability to do work, and work is done when something is moved. Now let's look at force. It says, have you ever tried to lift a very heavy box? As you pushed and pulled and struggled, you probably thought you were working very hard. But if you were unable to move the box, you did not do any work. That sounds really sad. If we weren't able to actually move it, we didn't do any work. But technically, according to our definition of work, work is done when an object is moved. So if we pushed or pulled on that heavy box and weren't able to move it at all, then we technically didn't do any work. You did not exert or put forth enough force to move the box. Force is a push or pull on an object. There are forces which sometimes prevent work from being done. One of these forces is gravity. Gravity is the force which draws things down toward the center of Earth. The weight of an object is determined by the force of gravity on the object. Remember when we were talking about the moon and how it has a different amount of gravity than the Earth does, and then the sun has another different amount of gravity, and that's why our weight here on Earth is not the same amount of weight it would be on the moon, or if we were able to actually get all the way to the sun. In order for you to lift something, you must exert more force. Remember, force is push or pull on an object than gravity does on that object. If a box weighs 15 pounds and you exert 14 pounds of force, you will not be able to lift the box. So let's review those terms again once more. Energy, it's the ability to do, that's right, work. Work is done when an object is, moved. Force is a push or pull on an object, and gravity is a force that, draws things down toward the center of the Earth. We'll come back and read this state bird card about the common loon in just a moment. But let's turn the page and keep reading here. I just did some work. By moving this page, I did some work. Now, there are two kinds of energy. So remember, energy is the ability to do work, and there are two kinds of energy. The water in the stream that rushed by Ben was moving, and all moving things have energy. A baseball zooming out to center field is full of energy because it is moving. Some objects which are not moving have the potential of moving. They have energy stored in them. The energy in these objects is ready to be used. This kind of energy is called potential energy. So if you're sitting there right now and just reading along and listening as I read this to you and not moving at all, you have potential energy because you have energy inside you, stored inside you, that is ready to be used but isn't currently being used. So that's potential energy. So if you stretch a rubber band to its full, it is full of stored energy or potential energy. However, as soon as you let the rubber band go, its stored energy becomes, that's right, moving energy. So I've got one of those rubber bands here, and if I stretch it out, is it moving right now? No, but it's got all this potential energy that if I let it go, all of a sudden it's got moving energy. However, after it's done moving, then we've kind of come back to our potential energy. So we've got potential energy, it has the potential or the ability to move, and then all of a sudden, if as I let go, we have moving energy because the rubber band, or in this instance it's a hair tie, is moving. So we've got potential energy, moving energy. The water stored up behind the dam also contains potential energy because of the Earth's gravity. If the water is allowed to spill over the top of the dam, the water's energy will change to moving energy. Energy is continually changing from potential energy to moving energy and back again. And we saw that with the example of the hair tie. Now, a lot of people have figured out how to use the energy of water, so let's read about that. Long ago, people found they could use water's energy to get things done. Water wheels have been used to run machinery since the time of ancient Egyptians. So we've got a picture of a water wheel here. The energy of moving water turns a wheel. Energy passed along from the water to the wheel, to the axle, and finally to the machine. The water's energy causes the machine to do work. Water wheels were once used to run a machine which ground grain into flour. Today, water wheels are sometimes used in small power plants to generate electricity. And so we can see that here as the water flows over the wheel, it turns the wheel, and then this wheel would be hooked up to some kind of machine, and that movement of this wheel would then power the machine. Let's keep reading. Steam is also full of energy. You will remember that when water is heated, its molecules increase in speed and spread farther apart. Heat supplies energy to the water. Steam expands to take up more space than the water it came from. 1 quart of water can produce 1,700 quarts of steam. And we have to look back in our book to see how that works again. Remember that steam is when water is in its gas form, and water in its liquid form is this. And so when these molecules spread out into the gaseous form to make steam, it's not necessarily creating more water, but it's spreading out the water molecules instead of having them packed so tightly together like they are in liquid. And so because of that, 1 quart of water can expand to 1,700 quarts of steam. If the steam is not given room in which to expand, it presses against the sides of its container with a great deal of force. When steam energy is used to do work, the steam is allowed to escape through a very small opening. As the steam escapes from its container, its energy turns a wheel, which transfers the energy to a machine. Steam power was once used to run railroad, locomotives, steamships, and machines for weaving cloth. Today, steam power is widely used to run generators which produce electricity. So let's read the something to do. Something to do, observing how a water wheel works. So we'll see you can observe how it works. To observe how a water wheel works, try the following demonstration. You'll need an old foil pie plate. So a tin foil pie plate after you've eaten the pie, then you can use it. Scissors, and a 6-sided pencil, or just an ordinary pencil works. Doesn't have to have necessarily exactly 6 sides. Cut the rim off the pie plate. Then cut 1-inch slits around the edge of the pie plate. Be sure to space the slits evenly. And fold each section to make the blades of the water wheel. And so see picture. So they've got the pie plate here. They've cut the rim off of it. And now they're cutting 1-inch slits all the way around the pie plate. And then they're folding up this edge, just one corner edge of each slit. Then, make a hole in the center of the pie plate and insert the pencil into that hole. Holding each end of the pencil, place your water wheel under a stream of water running from a faucet. Notice how the faucet water hits the ends of the blades, so these turned up parts, and makes the wheel turn. Now let's go back and look at this bird card of the common loon. So the common loon is the state bird of just one state, and that state is, that's right, Minnesota. And you can see where it tends to spend its summers. They can see a little bit of purple over here and on the edges here, so that would where it would spend both summer and winter. And you can see the light blue edging here, that would be where it spends its winters. The common loon is a large, heavy bird. It is rarely seen out of water unless it is in flight. Its feet are set so far back on its body that moving about on land is very difficult. In the water, however, the common loon is right at home. Because its bones are almost solid, it rides low in the water, sometimes almost submerged except for its head. It is able to use its wings as well as its feet when it swims after its prey. Common loons feed mostly on fish, but they also eat shellfish, frogs, and insects. In the winter, the common loon lives along the Pacific, so this area here, the Atlantic, and Gulf Coast, which is this area down here. In summer, it lives in lakes and rivers throughout the northern North America. Its weird yodeling wail is a familiar sound in these areas. And there are lakes around us that have the common loon that lives there. So this summer, or even now in the spring, if you're out fishing, you can look and see if you can find any of the common loons.